Okay, hello guys. I think it's recording. I'll put my laptop down. So today, we're gonna finally start with chapter 1 from analysis called sequences. Okay. So the definition of a sequence is a function whose domain is the set of positive integers. Okay. So when we talk about functions, within specifically the section of functions here, so I'm gonna review functions. So when you have a function, you have a domain and a range or codomain. Okay. So your domain, so since we are talking about real numbers, our domain is a real line or a subset of a real line. So it will be something like this. So for example, to a function could be f of x equals 2x. So if x is 0, let's say this is 0. So the function extended to 2 times 0 is 2. 2 is 0. If you got 1 here, 2 times 1 is 2. If you have 2, oh, 2 over here, no? If you have 2, 2 times 2 is 4. So 2, 4. Okay. So let me make it like this. So the domain is a real line, and your range is also a real line. Okay. So what you are creating is a relationship. Okay. So what you're creating is a set. Okay. So the function is really a set. Okay. It's a set that relates the couples. So we got 0, 0. We got 1 with 2. We got 2 with 4, and so on. Okay. So in general, you got x, f of x. X with f of x, right? So it's a set. So this is really your function. Okay. Is that the the function as a set? Function as a set or relationship or relation. Okay. So, but this is very infinite. Okay. So in particular, this is a subset of the real numbers cross the real numbers. Okay. That we use that notation, but sometimes we are lazy and we just say R2. So it means it has one element of R and another element of R. But in calculus, we learn how to graph functions. So what we do is you put the domain here. So you put the domain here and you put the range here. Okay, so this is let's make the domain green. Make the domain green. So this is my domain, and this is my range or codomain, right? So now I start making the couples. So who created this? I mean, maybe Euclides, because we call it the Euclidean space, right? So he said, put this 0, 0, this couple 0, 0, put it here. Put the 1, 2, you have 1, and you have 1, 2. So you make the couple, you put it here, you put 1, 2. Then the next one is put 2, 4, 3, 4. Okay. Well, it doesn't really look very 1, 2, 3, 4. Oh yeah, because I don't do exactly the same scale on both. 1, 2, 4. Okay. So it's gonna be like a line over here. Oh no, no, it's not. It's a. Oh, I should put this in wrong. So okay, so this is 1 and 2, and 2. This is 1, 2, 3, 4. So one that I'm looking for is the one, right? Okay, you see, this is a line, right? It's a line. It's a line. Because if I put all the other points here, I'm gonna get this, right? So that's why the representation of this f of x equals to x is this line. Okay, let me make it look like that. So so it makes more like a line. Otherwise, look like a curve. So yeah, you know what? You have done this many times. So okay, so the important thing is this, right? So a function is a relationship. It basically is a set that associates domain with the codomain and is a subset of R2 that we call it a Euclidean space. And then we have this graph associated to it, to the concept of function. Okay. And we're going to use that a lot. Okay. So a sequence is different because a sequence is a function that says here, a sequence is a function whose domain is the set of positive integers. So uh, so you're gonna graph the domain is the set of positive integers. So you start, don't even start at 0, you start at 1, 2, 3, 4, 5, 6, 7. Okay. And uh, let's say we choose f of x equals ln of x. Okay. I need to come my. Okay. So my domain is the positive integers. And if my function is ln of x, so we all know that ln of x look like at 1 is 0, right? and it goes like this. But so ln of so so we got like ln of 1 is 0, 2 is ln of 2, 3 is ln of 3, 4 is ln of 4, 5 is ln of 5, 6 is ln of and so on. So my set, the representation of this is 1 ln of 1, 2 ln of 2, 3 ln of 3, and so on. In general, we're going to have x ln of x, right? Oh, more than x, let's call it n, or m, let's call it m. M ln of m. Okay, so that's your function, but of course that's very tiring. So that's really what a sequence look like, but it's very tiring, and I wanna make it look easier to understand. So what I'm gonna do is I'm gonna focus on the real line only, and I'm gonna call this guy A1. I'm gonna call this guy A2. I'm gonna call this guy A3. I'm gonna call this guy AM. So some people would like to say this. So AN equals F of N. Okay, so that's the standard notation. So we don't get this point. So you get, but now notice this is the difference. This is the range. Okay, so this representation is this red one over here. So these two doesn't touch, no? So I got ln of 1 is 0, ln of 2, ln of 3, ln of 4, ln of 5, ln of 6, ln of 7. So that's what I get here. So I I lowered it down, and that's what I get here. So I got ln of 1 is 0, ln of 2, ln of 3, ln of 4, ln of 5, ln of 6, ln of 7, ln of 8, ln of 4, ln of 9. So you see, start moving slower. So this is A1, A2, A3, A4, A5, A6, A7, and so on. Okay? So something you can see, because we're going to talk about the limits, right? And at some point we should define limits here. In the book, let me see. But yeah, probably in the book. Just at some point we're gonna define limits. Let's see. Or maybe right now it's avoiding constant limits, right? But if you took calculus, I'm gonna say it, right? So you see this sequence is growing and growing and growing and growing and growing. Very slow. The slowest possible because it's ln of x. The ln is the inverse function of exponential function. So when something grows exponentially, like population growth, okay? So remember, there is a famous model, a differential equation. Okay, that let's say P is the population, and the assumption always is that the rate of change of the size of the population is a constant times the population at that time. Okay. When we solve when we solve this differential equation by integration, this calculus. I mean, you took calculus, you took differential equations. You have exponentially, so it grows exponentially. So exponential function is the function that grows faster exponentially, and ln is the function that grows slower. Okay. So something here interesting is that you take the limit of ln of m when n goes to infinity. This is gonna be infinity. So we said the sequence is unbounded. Okay. So there is this duality between sequences and functions, right? And is very important. So we wanna make sure we don't forget about it for interpretation. Okay. So this is really be our interpretation of sequences. So basically, our interpretation is an equals f of n, for f a function. Okay. So that's introduction to functions very fast. Okay. But this part of relation, we if you look at the book of Ted Sustrom, that is free book online. That's why I follow it. You can find whole section of relations. I mean, at some point, you just go back to what you need. You cannot just read the whole book, right? But in case you're curious, you can take a look. In case you want to do some exercises. Okay, so we have sequences. So from now on, we're gonna, instead of writing one half, one third, 1/4, 1/5, and so on, we are gonna call it 1 over n equals 1 to infinity. Okay, that's gonna be the notation. So notice how we have reduced the whole thing, because it's supposed to be like this, 1 ln of 1, but this is redundant. I know the position, right? So people said, okay, since I know the domain is already positive integers, I don't need to do all that. Okay, and a function is very complex because when I have not the integers but the real numbers, I don't really know who is next, who is after 0, 0. I mean 0.0001 comma 2 times 0.0001. Okay. I have the symbols on my Zoom connected. So every time that I move my hands, it gives some reaction. Oh, it doesn't show reaction. Okay, this one shows. Come on, it's showing. Oh yeah, there. So okay. So to what you guys not connected with me, so you can give me thumbs up. Okay, so that's our sequences, right? So you study this in calculus 1. We're gonna do here study then, but we're gonna do serious study, like we're gonna prove stuff. Okay. So let's do, for example, this sequence, example 2, let's call it. Let's say this is example 1. So for example, the sequence is 1 plus minus 1 to the n over 2. This n equals 1 to infinity. So what do you get? So you need to evaluate that 1. If you evaluate that 1, minus 1 to the 1 is minus 1, 1 minus 1, 0. You evaluate that 2, minus 1 to the 2 is 1, 1 plus 1 is 2, plus 2, 1. At 3, minus 1 to the 3 is minus 1, 1 minus 1 is 0. So you get 0, 1, 0, 1, 0, 1, and so on. Okay? So that's the concept sequence, and the behind of this, we're gonna do this. Since this is survey topics, I can just jump here and there, but the idea is to prepare you for the future classes in graduate school. So after sequences, I'm gonna do series. Okay, I'm gonna talk about convergence of series. Okay, because because this, I'm not gonna do something we're not gonna do in this class because it's survey. I'm not gonna spend a lot of time proving the main theorems. I'm not gonna prove the Bolzano-Weierstrass theorem. I don't think I'm gonna prove the main value theorem, the role theorem. So calculus analysis 1 is a calculus 1 well done. Like in Germany, they call it analysis 1. They don't call it calculus. I think in Germany, they start doing the epsilon, the deltas, all that. And that's your calculus 1. So she called it, I remember I have a friend from Germany, and she said, we're just saying calculus 1. They said, no, that's analysis, but this is the same thing. So our calculus in the United States is more techniques. We don't do epsilon, deltas, convergence, all these things. In Germany, it seems like they just do the whole thing together right away. So we're gonna do next, and here in this book, this is the concept of limit. Okay, but in this chapter, he's not talking about limits. I'm gonna talk about limits because that's the language you use in calculus 1. And I'm gonna take a look to my books from calculus, and I'm gonna go there, and we're gonna compare because you will see some epsilons and deltas, but we in calculus 1 you kindly don't touch that. We don't want to scare students, but it's there. So I'm gonna get some problems from there, from your calculus 1, from Stewart, from typical books, and you'll see that this concept is there, concept of convergence, but the concept of convergence is the limit. But since we are doing analysis, people don't want to call it limit, just like that. Okay. So this is definition. So a sequence is then n equals 1 to infinity converges to a real number a if and only if for each epsilon bigger than 0, there is a positive integer capital N such that n bigger or equal than n, such that for every small n bigger or equal than n, we have absolute value a n minus a is less than epsilon. Okay, so that is really saying this, but this book doesn't say it. I don't see any limits there, but this is what it is. This is the limit of a to the n when n goes to infinity is equal to A. This is what it means. That's what you saw in your calculus class. But I think they want to say, I think the books want to say, that maybe saying, I'm not going to tell you that this is the limit. this is this is the real thing. This is I'm going to avoid the name limit, and you see, this is the real thing. Okay. So what does it mean? So you have an A. Well, before that, you have an A. Well, you have an A, and you have the sequence. Okay. But turns out that the sequence converges to real number A. That means, what does it mean? It means that most of the sequence must be close to A because it's converging to that, right? So maybe you have some elements here, a few elements there. But if the sequence is converging to A, it must be close to A. Okay. So that's where we use the concept of epsilon. Because it's saying here, A minus A is less than epsilon. Oh, perfect time to use our notation, our propositions from previous classes. What does it mean? What does it mean? So you're going to stop. This is a quiz, fast quiz for you, 2 minutes quiz. What does it mean? AN minus A less than epsilon. Using your propositions that we proved in previous classes. Okay, what does it mean? Graphically, show me what does it mean. A for n bigger or equal than n. Ready? Okay, I'm gonna tell you. So this means that an minus a is between epsilon and minus epsilon for n bigger or equal than n. But when I add a to both sides, I got minus epsilon plus a n plus epsilon plus a. Okay? So what does it mean? It means this is my A, and you add epsilon to A, and you just add epsilon to A. Okay? So for n bigger or equal than n, so that means for only an section of finite numbers of n, okay, n can be 1,000. So I have 1,000 outside of here, right? But after that, all those guys are inside here. That's what it means. Okay? So you see the difference? This doesn't say anything. I mean, the book is right. I mean, what is that? So it's the real meaning is all this what we're doing over here. Okay, but since it's calculus 1, that's what we tell our students. So we explain this, right? We explain this. So this is probably the connection you have. But as you see, there is kind of the absolute value behind the epsilon, the capital N. Okay, so somehow we're hiding stuff in calculus 1, and we just teach you to do tricks. Okay, that's what engineers want. Okay, they don't care about so much mathematical details. Okay, so so really, when you want to prove that the limit of something is when you have a sequence, right, and you want to prove that limit, the limit of the sequence goes to that number, you have to do a lot of work. Okay. So yeah, so I was thinking an example. I think the book is doing the same example. So let's do an easy example. So how you really prove, okay? Mm, so example, show that 1 over n goes from n1 to infinity, converges to 0. So basically what I'm asking you is show that the limit of 1 over n when n goes to infinity is 0. Okay? We know that. Why do we know that? Because if you graph the function, right? This is f of x ln of 1 over x, sorry, is positive. So I don't care about the negative. The negative will be like this. So I don't care about this part. But then I go point by point. So it will be 1, 2, 3, 4. So this 1/2, sorry, 1/2, 1/3, 1/4, and so on. So I know that this 1 over n equals 1 to infinity is 1, 1/2, 1/3, 1/4, 1/5, and so on. Okay. So I can tell that this guy, so you see that this function goes decreasing and it's gonna go to 0. I'm using my calculus one because I need some intuition. It's like you don't know mathematics. I mean. So that thing go to 0. So what does it mean? So when I do it here, this is 0. So you got 1, 1/2, 1/3, 1/4, 1/5. So all these points are getting closer, 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 closer to 0. Okay. So I need to, so what I need to do. So it's saying for each epsilon, so any epsilon. So you give me a small number. So let epsilon a fixed real number. Okay. Let epsilon be a fixed real number. Then, so let's say epsilon is like this. This is epsilon. And this is minus epsilon. Okay. So how can I know what is let's epsilon be a fixed real number, also very small. Also very small. Okay. Because if it's big, I mean, obviously all the sequence is bigger than 1, all the sequence is gonna be there, right? Okay. So there are ways to do this. And let me say like this. So that's those part are gonna some faculty or some teachers will say you need to prove that. Okay, let's see. Let's see what you think. It must be, or there exists capital N. Actually, this is a property, okay, from the real numbers. But there exists capital N such that 1 over n is smaller than epsilon. Okay. And why? Because if you switch 1 over epsilon is a big number. Right? And there is capital N bigger than 1 over epsilon. Okay. Why? Because the natural numbers or the positive integers is not bounded. Okay. So you give me epsilon a million. Well, no, 1 over epsilon a million. So epsilon is what is 0.00060.1, right? Right. So 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 I can find n such that capital N is bigger than 1 over epsilon. Otherwise, epsilon will be abounded for the abound for the positive integers or the natural numbers. The natural numbers are not bounded, are infinite. That's something you can prove. That's some things at some point you have to agree that some things are reasonable. But if it's a proof, you can test. So this is true. So there is an n such that 1 over n is less than epsilon, right? So it says here, a sequence A should then converges to a real number A if and only if for each epsilon there is a positive integer n such that n bigger or equal than n. We have a n minus n less than epsilon. Okay, so I think we found our n. I just call it capital N, but because I'm pretty sure that's correct. So let's see. an minus a. We need to prove that this is less than epsilon. So an minus. So what is an? An is 1 over n. Minus a is 0. So what do I know is 0? Because I know it's going down, right? So it's going to 0. And because I know that from calculus, but I never prove it probably. So 1 over n minus 0, it's just 1 over n, right? But now, notice this. 1 over n is less than 1 over n when this is true. When 1 over is less than n, 1 over n. When n bigger or equal than n. Because if we invert these guys, yeah, then 1 over n. Oh, well, sorry, let me put it. So if we invert it, 1 over n bigger or equal than 1 over n. Because when you invert the numbers, the inequality changes, right? So that's something you know from calculus. You can prove this. Again, this class is for that. Anything that you haven't proved ever in your life, try to prove it. And if you cannot prove it, let me know. I mean, this is easy to prove. Okay. How would you prove that? So think to 1 minute. Ready? I will do this. So n bigger or equal than n. I'll divide both sides by n times divided by n. This is a positive integer. A positive integer doesn't change the inequality when you multiply both sides. That's a property of the real numbers. Okay. Again, everything. Remember. So let's finish. So this is 1 and chance. You see, 1 over n is bigger or equal than 1 over n. I remember for real numbers, this is the great thing of real numbers. All that we know from real numbers are the axioms we wrote in this class. Okay, so pretty much everything that you say about the real numbers. Sorry, I'm gonna go back to the actions where we put it. These actions. Everything we said from the real numbers is here. Have a sum operation. You see, R is distribution, all that. Okay. So whatever is not, it says here, look, if you add both sides, the sum doesn't change. Okay. If you add on both sides, the sum doesn't change. You have transitivity, right? It's not saying anything about. Look at this. It's here. It's an axiom. Axiom 11. If x is less than y and c is positive, this implies this is true. The whole stays the same. Also, probably we will have to say if we haven't proved it, but so it's probably will be part of a consequence of these actions. If c is negative, the sign will change. And it's not saying here that you flip it, but you see, we're saying here that you can add. Okay. But adding many times is multiplying. So that's coming of the actions, but I let you get those yourself. Okay. So those are basic things that I have to keep moving, otherwise I'm gonna keep proving everything. But if you have any idea, let me know. So you see, this is true. So 1 over n, and I will say, I can say whatever I need in the definition. I need less or equal or yeah, it could be less or equal, right? And then I have chose n such that 1 over n is less than epsilon. So I have less than epsilon. Yeah, okay. I was worried that I was not sharing. Okay, good. Okay, so we have proved that indeed with a equals 0, the sequence a to 1 over n converges to 0. Okay. Okay, so let me see how much time I had done. Let's see, I want to do another proof. Let's do a theorem. We have a lemma and a theorem. Let me see which one I choose. So because if I do the theorem, maybe I need to do the lemma first. So let me see which one I choose. All right, there are some statements that I'm gonna state, but then I'm not gonna prove. So you can go to the book and prove it, or read the book. Okay, so we can advance. So okay, so let's do this one. It's called theorem. Well, let me say that it's a lemma. I'm not gonna do this proof. You can do it in read the book. So a sequence, but it might be useful for us for later. A to the n converges to A if and only if each neighborhood of A contains all but a finite number of terms of the sequence. Oh, I need to define what is neighborhood. Definition. What is a neighborhood? Definition. A set Q of real numbers is a neighborhood of a real number X if and only if Q contains an interval of positive length centered at X. And I know slides are popular, and probably you guys don't want to write this, but I advise you to write this. This is a memoristic process. When we're writing like this, we're memorizing stuff. That was the Newton technique. He has to write everything. And you see on conferences, faculty is writing everything. So if you can see something, they write. And we love workshops because we can learn something. At some point, no, when you're faculty, nobody teaches you anything. So you have to go to very expensive workshops, or you're a professional. You have to pay very expensive workshops to learn something new. Okay, so and people take notes. So take notes, okay, because you're helping to your mind to learn. Okay. Okay. So we were saying that a set Q of real numbers is a neighborhood of a real number X if only if Q contains an interval of positive length centered at X. That is, if and only if there is an epsilon such that X minus epsilon, X minus epsilon contains Q. So yeah, so X, this is X. And let's say Q is maybe this. This is this set, but with other things, with this and with this, okay? But this is Q, right? All this is Q. But then you can put around X, you can put an epsilon, you can put an interval inside of Q. You see, this interval is inside of Q. Even though it's not inside here, not inside here, but it's this part of Q and it's inside of that one. So that's a neighborhood, okay? So a sequence, the lemma is saying that the sequence converges to A. So this is A, and it says that any neighborhood, or basically, if you want to make it more radical, less general, it's like any neighborhood of A. So this would be a neighborhood of A because it has a little interval containing A. contains all but a finite number of terms of the sequence. So you have the sequence, but any neighborhood of A, any little interval containing A will contain most of the sequence. That's what it's saying. Any little interval containing A will contain most of the sequence if the sequence is converging to A. That sometimes is called the limit point. If A is a limit point of, well, limit point has another concept, but it probably is not better to mix those things up. So yeah, so the sequence is converging to A. So any neighborhood contains most of the sequence, except for a finite number. Okay, so that's a lemma. You can prove that. That's in the book. I'm gonna skip that one. I wanna kind of try to finish with two theorems. Okay, and then probably enough for this week. Next week I'm gonna start with Cauchy sequences. We're gonna do Cauchy sequences. Operations of sequences. And then I'm gonna start with series, okay? Because I don't know if you remember calculus 2. So calculus 1, calculus 2. In calculus 2, we learn series, sequences, series, and like you will see the Taylor's theorem. Any function can be approximated as a series, as approximation of a series of polynomials. That's what we're gonna get. Because you're gonna use that theorem, in your differential equations, ordinary differential equations, your partial differential equations, in your linear program, in your optimization problems, in your linear programming. So this is very important. So I want to get there. I want to make sure we cover that in analysis. Okay? And then we go back and then do continuity, and we do other things, maximum. But I'm gonna go sequences, series, and then we see why they're good for. Okay, I want to give you also the idea, what is this all good for? All this difficult mathematics, what is this good for? And you know, maybe I can give you an idea right now. So you can look it up. It's called Fourier series. Okay. So when you have series, so let's say you send a signal. Okay. So a signal could be something like this. It's like the signal is on, the signal is off. Signal is on, signal is off. Signal is on, signal is off. Okay. So the problem of this is this is not a continuous function. So all the mathematics we're gonna do in this class, the calculus is kind of very difficult to apply here in a general idea. Okay. Well, there's also Fourier series, and please look at it on YouTube. And that signal can be approached by a continuous thing, like what color should I use? Maybe blue. So it's gonna be something like this, and then here, and cheek, and then cheek, and then here. Okay. So that Fourier series is the secret, one of the secrets of communication, right? Today, people do many things, right? But a Fourier series, it could be sine series, cosine series, but let's say just something like this. It's something like the sum of an sine n pi x, no, pi x over n, something like that. Okay. So I know maybe that's a number wrong, but this looks pretty much look like that. And this is how this one looks, you see? Oh, sometimes it's better to, instead of sine, I can use cosine. But the whole point is, the bigger the n is, the more oscillation you get here, and the closer it is to your signal. And guess what is this A to them? That's called the harmonics. That's called the harmonics. So if you have a more complex signal, I say something like this, like your music, some music you're playing, this can be expressed as some Fourier series. And in your computer, when you're sending a song, I mean, it's supposed like today probably is done different, but one way you can do it is instead of sending the whole wave, the whole song, you just send A1, A2, A3, A4, probably the first A10. These A10 coefficients. So you don't have to sell the whole infinite series. You just send the first 10 coefficients as a pair, as a number, and an email, or a secret message. And over there, when you get the message, you reconstruct this whole signal. Okay? Graphing it. But in this, but you know, you do it with music or with images. So you reconstruct the whole thing with these values. Okay? That way you are saving capacity of the computers, etc. Okay, so that's what we're heading. These sequences are going to allow us to define series, and this series is somehow one of the secrets of communication. Okay, on images, you send a picture, depending on the number of pixels, you have divided the picture in a certain number of rectangles. Right? So you can have a really good picture if you send many rectangles, but if you just send not many, only 10, you're gonna hit your picture, you can recognize yourself, but you say, oh, this is not a good picture. But that's when you are not reconstructing with the whole series. Okay, that's something like that. Okay, so all this to say that this is useful, trying to motivating you because I mean, you're taking this class, you're already motivated to do math, but I wanna keeping you motivated. So there's one theorem, you know, and let's prove this theorem, and try to do it yourself. So in this, I'm gonna put it myself. It says if an n equals infinity converges to A, and also to B, then A equals B. So the sequences believe in monogamy. They only converge to one point. Okay. And this kind of, what? Of course, they had to only converge to one. Well, because we are on the real line, you are used to this. But easily, we can consider a sequence in another space, and that's not going to be the case. But I'm not sure if easily, because our intuition as human beings, probably, we want it like that. But I'm sure it's possible to create a space where this is not true. But look at this. If n equals 1 to infinity converges to A and also to B, then there must be equals. And it makes sense because if I have a sequence, and you said, okay, so my sequence, this is A, this is B. So yeah, maybe it's not like crazy. You said, since this is as infinite, right? Maybe the A2, A4, A6, A8, A10, the events are here, and the other ones, A3, A5, A7, A9, and so on, they're here. So the events are here, the other there, so everybody's happy. It converges to two different points. Well, it doesn't work like that. You can have two different sequences, so they're called sequences. You had two different sequences converging to two different points, and you know, and we have to see something that is gonna call Cauchy sequences. The idea of this math is to avoid that kind of stuff, not too much freedom. So they want monogamy. So so um, how can we prove this? So let me give you 5 minutes to do that. So stop the video and, try to prove it. Or let me give you those 5 minutes. Okay, so let's try to do it that. So the class is really 1 hour 50 minutes, and I don't get extra your time. So let me give you 3 or 4 minutes to do. Okay, sorry, I'm gonna let it run, and I'm gonna give you 4 minutes. Meanwhile, I go get water or something. Okay. Okay, guys, so let's do it. So we're gonna do it by contradiction. Okay, so we're gonna do the following. It seems, it seems obvious to us. Let's try contradiction. When something looks obvious, so assume A is different than B. Then the distance between these two, so B minus A is, or A minus B, that's the same, is bigger than 0. So let's take the distance here, okay? And then let's take neighborhoods around A and around B. They don't intersect like this. Some two neighbors, okay? So I can do, this distance is this. So I can do like half or 1/3. 1, 2, 3. 1, 2, 3. Yeah. So maybe I can do that. So just to make sure they don't intersect. I mean, I could do B minus A half, but yeah, let's make, I mean, so you believe me more. So let epsilon equals to B minus A thirds. So you see, I'm gonna get, this is my epsilon, B minus A thirds, and this is gonna be my epsilon, and this is B minus A thirds. B minus A thirds. So, sorry, my kid was giving me food. So, okay. So we do the following. So this is your epsilon. Okay. So by this lemma, you see, I think we're going to use this lemma. Each neighbor of A contains all but a finite number of terms in the sequence. Okay. So by this lemma, my lemma, the neighborhood around A, that would be what? A minus epsilon, A plus epsilon contains all the sequence except a finite number. And similarly, B minus epsilon, B plus epsilon contains all the sequence except a finite number. Okay? Because both are neighborhoods of the limit, and we have two different limits. But this is a contradiction. This is a contradiction. Since the neighborhoods do not intersect each other. Okay. So since the two neighborhoods don't intersect, you see from the beginning, that was kind of my argument. So I'm gonna make a neighborhood for A, I'm gonna make a neighborhood for B. They don't intersect because B minus A thirds, there is a distance between here and here. There is a distance of, between neighborhoods, there is a distance of B minus A thirds. Okay? So there is a distance, they don't intersect. So by the lemma, most of the sequence must be in one side and most of the sequence must be on sides. Impossible. They cannot be in both places at the same time. So that's a contradiction. Therefore, A equals B. And remember, I told you the contradiction argument, right? It was like A implies a contradiction, then no A implies a contradiction, then A. I think that was the statement we did, right? Contradiction. And in the book it's 116. Yeah, that's what we did. Well, let's not say no A because we said no X. So the statement is X, no X, plus X. Because A, since I'm using A and B, is kind of okay. So so I think we can stop here. It's a lot already. And no, let me leave this. That's contradiction. So I'm gonna give you a homework, but no, this homework is for exercise. It's more exercise for you. The homework, I'm gonna sign it. So I'm gonna give you a week to finish that one, and then you're gonna have a specific problem that you have to type in LaTeX. Okay, and that one has to be very well written, very nice, very clear. Okay, and okay, so but this is my exercise for you for this weekend, theorem. So you think when you're driving this in this theorem, if AN converges to A, then AN is bounded. Okay. So yeah, so try to prove that. So that AN is bounded means that there is an M such that AN is less or equal than M. That's what it means, bounded. Okay, for all the N's in the natural numbers of the sequence. So all the sequence must be below an M. So if AN converges, it must be bounded for some M. Okay? Okay, so I'll let you do it. We'll think on that. And then next week we're gonna do Cauchy sequences. An operation with sequences, and I will start series. Okay? So we're gonna do series to help you for not only one class, not only for analysis, but for other classes. But also, this is just analysis. More proving. And it's gonna be useful. Okay? Okay. Thank you guys.